Reducing discretization error. This video is part of a course on food physics, of which this belongs to the modeling section. It is the third of a 5-part series on error, uncertainty, and validation. Here we're going to discuss how to keep track of discretization error that happens because of numerical calculations of the differential equations and reduce them. Basically, we'll have a very simple and informal way to talk about mesh convergence. So there's lots and lots of literature on this. It's a very matured subject. I'm not getting into the numerical aspects, the theory or any of that. Just a very simple way of how to implement it. The following video, that's this one, is going to give an overview of the simple ways to estimate uncertainty. Models have errors. So in modeling, we start with the reality of interest, and modeling process leads to a mathematical model that is typically a governing equation, boundary condition. Then we implement it in a software for numerically solving this governing equation and boundary condition. That's our computer model. And then the computer model gives results that look like this, that all of us have seen. And those are my simulation results. Now we all agree that the solution to our problem, let's say the solution to this mathematical model that we have, this solution should be independent of the solution procedure, however way I am actually solving. The software implementation, the particular numerical methods used, and so on should not determine its final solution. The solution should be independent. That is the basis for this discussion, that the numerical errors, the errors that we make, we need to ideally we would like to eliminate them. We want to get an exact answer to this, but this is not possible. By the very nature of the solution process, this is because it's a numerical solution, we cannot get an exact answer. So let's see how we can reduce this error. Repeating, the solution must be independent of the mesh. So if we have a geometry and we mesh it two different ways, the two different ways are going to give two different solutions, or can give two different solutions. So then that's not okay, because my solution should not depend on my solution procedure. If you're not familiar with what is called a mesh, you can look up anywhere. In this example, we're using the finite element method, which is one of the many numerical methods, where the mesh is a collection of nodes that are the vertices of these triangles, and those nodes make up an element. So this is a triangular element over which the solution is done. The computations are done, and so basically it solves at the nodes and interpolates anywhere in between. So how do we make sure that this solution is independent of the mesh? Mesh isn't messing up the solution. How do we make sure of that? Now, the nature of these computations are such that the finer the mesh we make, the more accurate the result is, generally speaking. So an obvious solution is to calculate more more points, meaning make the mesh as fine as we want, so our interpolations are better and our results are more accurate. But that is more computing. So when do we stop? So we have some sort of a balancing that we need to do as we keep going finer and finer mesh. We keep increasing the amount of resources that we need. Is it causing enough improvement in the results? Is it causing improvements that we can see? So how do we decide that? Can we do better than just eyeball? That's just looking at it, oh, this result is fine enough. It's not improving anymore. Can we do better than eyeballing? Can we just do this a little more methodically? That's what we'll talk about. A mesh convergence plot is simply an easy way to see the mesh independence. So to do this, we just start from somewhere. We just have a mesh to get started, refine the mesh, and then create a plot of whatever is it that we are interested in from the model, that variable versus the different meshes as the mesh is refined. So let's look at little more detail. So we choose a mesh initially. So you may wonder, how do I get the initial mesh? There is no formula available to choose a mesh size for a particular situation. It is often left to the software for automated generation based on the particular physics and the geometry. So there are rules that the people have accumulated over the years that have been implemented in the software, and so it will do a mesh initially based on the particular physics and geometry. Generally, we should make a finer mesh where the changes are greater. So with that, you solve. And you look at the solution. If the solution doesn't even look realistic, even just a sort of a common sense way of looking, then it's obviously not right, and we probably need a finer mesh, so we go this way. But if the solution looks realistic, then we have to have this question, is it converged? So in a minute I will show you how we can plot it. That's the mesh convergence plot. But if it is not converged, then we just repeat the process. So by doing this, you're getting a solution every time, and you plot that with some mesh parameter, mesh size or the number of elements and so on. And so we'll see this in just a second. We can go through, this is all that is in the mesh convergence. Here is an example of a mesh convergence plot. So here we're calculating average moisture in a drying process, average moisture versus time. Now, when we are solving for many variables, we really have to decide which variable is it that we want to plot. Choice of variable can depend on the most relevant ones, like for temperature, for example, temperature for sterilization, or the degree of sterilization. In case of drying, it's average moisture, for example, or moisture in a particular location that is very critical. So the variable needs to be chosen that way. Variable can also be chosen based on which variable is the most sensitive with respect to the mesh. that also can be a way to decide which variable. Now, you plot that variable, which in this case is average moisture, for different number of elements in this case. So as the number of elements is increasing, the mesh is finer. So you notice all of these ones, especially after the green, most of these are on top of each other. So it's on top of each other. And so that means by going finer and finer mesh, I'm not getting any better results. However, it's going to cost us more in terms of computing time and resources. So that's why we end up deciding whichever one is the least number of elements that gives a result that does not change anymore. So this plot, the overall plot of a quantity as mesh is varying, is called a mesh convergence plot, and it's very critical because it is this one that is saying that, look, your solution, your results no longer depend on how you chose the mesh or how fine a mesh you chose. That is very critical because our final answer should have nothing to do with the solution process, that is the mesh that is used to solve. So when there are many variables that we're computing, especially when there's multi-physics, different types of physics like heat transfer and electromagnetics that we are computing, things get more challenging or can get more challenging. Ideally, each variable should be checked for convergence independently, even for within the same physics. When we have separate mesh used for different physics, then definitely we have to perform separate mesh convergence for each of the physics, choosing a variable from the relevant physics. And so even if we have the same mesh used for two different physics, then we should check one variable from each physics and do a mesh convergence plot to make sure that that physics is converged. Before we go any further and kind of complete the video, now is a good time to perhaps pause the video and think of what parameter would you choose to monitor mesh convergence for your model, assuming you have a model in mind. That's why you're watching this video. So if you have multi-physics, for example, then which parameter would you choose for each physics to monitor mesh convergence? This would be a good time to think about that. Mesh convergence can be automated, and it is automated in many software. We typically don't end up using it for research because we want to have more control, and it may not always be available in a software. But what is the main idea behind an automated mesh convergence? The idea is not too difficult. So we start off a computation. So let's say this is a heat transfer computation. This is my domain, and this is my domain, and I do a mesh, and then I get a set of results. So from the results itself, the results will kind of guide us to see where the variables are changing most, where are the gradients the highest. So wherever the gradients are highest, then those are the regions that you put more elements and repeat the process. So you keep doing that. You keep doing that with more and more elements, and again until your solution does not change anymore. So this can be automated because from the initial computation it can estimate the gradients, and wherever the gradients are higher it puts more elements in there. To summarize then, discretization error has to do with the error made in solving the model equations using numerical methods. Now, how do we keep track and thus try to reduce this discretization error? Is we start from somewhere, start from a mesh, and that is reasonable, and then refine the solution and keep doing this until it doesn't change, until the solution does not change. How do we do this in a methodical way? Is we plot some important variable of our interest in the model and see whether the variable is changing as we are refining the mesh. So we plot the variable as a function of let's say mesh size or the number of elements, and that kind of a plot is called a mesh convergence plot. And so from the plot we infer, okay, going any finer is not going to give us anything, it will just increase the amount of computing. In the big picture of things, where we are developing a model that is a reality of interest replaced by a set of governing equations, and then we are solving the governing equations, these, using some sort of a software in a computer to get plots like this. In this process, what we just talked about, reducing discretization error, reduces the error between the mathematical model and the computer model. That is the true solution of these governing equation and boundary condition, and what we actually get. We reduce that. The very, very important point here is while this is critically important, it does nothing to the errors that we have already made here in formulation. So in this step, in formulating, we made error because we replaced reality with a mathematical model, and that error it stays with the model because we are starting from these equations. So this error has not, does not get addressed by reducing discretization error, just to keep the big picture in mind.